Swayam Prabha. Digital India. Educated India.
So this course I've tried to focus it on integrated millimeter wave systems. So we will be starting from applications, then going through some demands that the application imposes, and then understand the technology constraints that we are working with, and then move on to actual design. So just an introduction, let me introduce myself, right? I'm Arun Natarajan, and a long time ago, I got my bachelor's at IIT Chennai, and I went to Caltech for a PhD right after my undergraduate degree, and I worked on integrated millimeter wave transceivers there. From there, it seemed a good idea to get some industry experience, and at that time, millimeter wave ICs were just becoming commercial, or people were interested in building them for Wi-Fi equivalent applications. So I went to IBM Research for 4-5 years and did that. And then I moved to Oregon State in 2012, where I've run a research group and I teach analog RF millimeter wave integrated circuits. I've also been involved over the last few years with a company that is building commercial 5G beamformers as well as satellite communication beamformers at frequencies ranging from 20 gigahertz to 60 gigahertz. And this experience has also been a fantastic one to understand the industry implications of the kind of stuff that we were doing in academia. Just to complete the thread on my research itself, so we'll talk about this right at the end of the course, but these are some of the problems that are now gathering research attention at millimeter wave. There is a need for a lot of these RF and millimeter wave systems to operate in congested environments, or in environments where the transmitter and receiver are enabled at the same time. So there is a need for interferer tolerance. So that's one area that we work on. And broadly speaking, both from RF to millimeter wave, if you think of it as a continuum, the world is moving towards using these radios, these transmitters and receivers for communication as well as sensing. So we do a lot of research in my group on bringing the sensing aspect of it in and trying to do some signal processing at RF as well. So why are we talking about millimeter wave at its core, right? What is happening? Why are we talking about millimeter wave and in general this demand to push to high frequencies? If we look at the way that wireless systems have evolved over the last perhaps 4 decades, right? So initially in 1G, we designed systems that were primarily for audio, so telephonic links. And then gradually we added text to it, SMS, and then eventually a little bit of data by the time we got to 3G. But then as we got to 4G over the last 15 years, data has completely taken over, right? And these systems are being engineered to support extremely high data rates. And along with this data rate, there is a lot of discussion about what the peak data rates are for these systems. But in reality, most of what people are also trying to optimize is what is the data rate that 90% of the users get 90% of the time, right? So those kind of data rates, if we want to optimize, we need to have a lot of throughput in our system. And moving to higher frequencies in 5G and 6G will potentially enable that. So we'll talk a little bit about that. So what we see emerging in the future is the whole network as a sensor, where you would have the same radios performing communication as well as sensing. and with a very heavy emphasis on all of this happening with very low latency. So you can imagine applications such as virtual reality demanding very low latency in the system. And the kind of millimeter wave radios that we are talking about target these type of applications where you could be communicating, sensing, all with very low latency. And so we will be, from a system perspective, looking at what it takes to communicate and also what it takes to sense. So we'll look at both of these applications. So the initial outline for today is here. We'll begin by talking about applications and then just take a very quick high-level view of transistors, passives, and interconnects. We'll talk a little bit about lumped versus distributed systems. And then from there, we'll try to understand the constraints of what can be done on silicon and compare that to the link budget that is needed in order to establish any of these links or sensors. And then move to an important concept of phased arrays, about how we can solve some of the limitations of silicon technology by doing things that silicon technology excels at, which is you throw transistors at the problem because the incremental transistor is near zero cost. So we try to take benefit of multiple elements in order to meet the link budgets, and then we'll get into the math of array patterns and understand from array patterns how that translates as specifications to the IC designer themselves. So as I'm sure many of you are aware, the heavy lifting of spectrum today is carried out at frequencies that are lower than 6 gigahertz, right? That's where the cellular networks operate. That's where the Wi-Fi networks operate. The Wi-Fi is now beginning to approach 7 gigahertz. But in that area, or what we generally call the beachfront spectrum, this is where we have most of our wireless systems operating. But there are a lot of legacy users in this space, and allocating new spectrum every time here involves a lot of negotiation with existing stakeholders. And as a result, the spectrum allocation is quite fragmented. You'll get a little bit of spectrum here and there. And you can see, for example, that what is considered a very wide bandwidth would be 160 megahertz, where we are combining many smaller channels together in order to support high data rates. And since the channel bandwidth is small, in order to support high data rates, we need very high order modulations. And in order to receive higher order modulated signal, we need much better SNR. So this causes what we are calling the RF spectrum crunch. And in this landscape, moving to higher frequencies seems very attractive because of the large spectrum that is available. So for example, at 60 gigahertz, there is 7 gigahertz of spectrum that is available. In the E band, which is the 71 to 76 and 81 to 86 gigahertz, there is 10 gigahertz of spectrum that is available. So now we can see that we can have much higher channel bandwidths that are of the order of 2 gigahertz. And with these high channel bandwidths, if we just want to use even a low order QAM modulation, we can achieve really high data rates, right? So with much lower complexity of modulation, we can achieve much higher data rates because our bandwidth is high to begin with. And this has led to a lot of interest in enabling systems at millimeter wave frequencies. So technically, millimeter wave is where a lambda is of the order of a millimeter. So at 30 gigahertz, you have lambda of 10 millimeter, and then 300 gigahertz, you have lambda of 1 millimeter, right? And beyond this, we call this sub-millimeter wave. But you will see that both this boundary and this boundary are a little fungible. So people will design 25 gigahertz or 20 gigahertz systems and still call them millimeter wave. because they are quite close to that 30 limit. And similarly, at the upper end, millimeter wave and submillimeter wave. If you read papers, for example, the nomenclature is quite mixed. But the key takeaway is, in general, you have large bandwidths that are available at these frequencies. So, in addition to this, an interesting property at millimeter wave is that the wavelength is quite small. And so, if we are trying to build multiple antenna systems, then the physical size of the system is quite small, right? Because typically our antennas are, the antenna size is proportional to lambda, and the spacing between the antennas is proportional to lambda. So you have an overall system size that scales with the wavelength. So if our wavelength is coming down, overall size of the system is coming down. This is particularly interesting if, for example, I want to put a MIMO system inside my tablet or laptop, for example. I can easily put a large element array inside pretty small form factor devices, because the physical size of the system is quite small. So just to give some examples of the frequency allocations in 5G. So there are some band nomenclatures that are, again, these are non-technical but worth remembering in general. So we have the frequency range 1 or FR1 frequencies, and these are examples of some of these bands. And yet again, I want to emphasize, if you look at the bandwidths that are there, these are of the order of tens of megahertz to 100 megahertz, those kinds of bandwidths. These are not large bandwidths, right? And if we look at the sort of each channel bandwidth that people are talking about, they are typically in the 5 megahertz to 10 megahertz in the lower range of these frequencies. And then as we move to a little bit higher range of frequencies, there is a larger 100 megahertz type of bandwidths available. So these are the applications include providing wide area coverage, or basically coverage in urban and suburban environments. But if we look at what is called the frequency range 2, so allocations in 5G, right? So you can see here that these bands, the N257, 258, 260 bands, they all have gigahertz of available bandwidth inside them, right? And then as we move further to the E band, there is 5 gigahertz for uplink, 5 gigahertz for downlink, right? The bandwidths that are available. So with these kind of large bandwidths, the standards support channel bandwidths that are of the order of 50, 100, 200, all the way up to 800 megahertz. And so in terms of, for example, cellular data rates, we can support much higher throughput in FR2. And as we move forward to even more applications, such as what is called fixed wireless access, which is basically wireless links that are delivering internet in the last mile to homes, for example, things like that, or AR, VR applications where you have extremely short ranges but gigabits per second data rates. That's where these FR2 frequencies and E-band frequencies are expected to operate. So to sort of summarize all this, we see the impact of spectrum congestion and low available bandwidth, but we can put it all together through the concept of Shannon capacity, right? So the capacity, if you have just a single transmitter receiver pair, is given by this, right? And so now if I want to increase the capacity that I have in my network, my options are to either increase the bandwidth or improve this SNR, right? Those are my only two options. Now, if I move to a MIMO system, right, I can have this go up as a certain n, right, where let's say I have n THs. So I can do this if I have MIMO streams, but then I'm basically asking for multiple antennas, right? So my choices are either increase bandwidth or go to MIMO systems with multiple antennas, or figure out a way to improve my SNR. But you can clearly see here that improving the SNR only has incremental impact because it is inside the log, right? Whereas if I double the bandwidth, then I'm actually doubling my capacity. So it's much more attractive to operate with higher bandwidth or with MIMO systems. And if you look at gigahertz frequencies radios, they have gone to MIMO systems, right? Even your Wi-Fi is MIMO and all your base stations are MIMO. And at millimeter wave, we have the advantage of larger bandwidth, so we want to move there. As we just noted, if I am increasing, if I increase number of elements, right, what I see is that my size is proportional to some wavelength, right? So this would imply that as you increase the frequency of the radio, lambda will decrease, so overall size decreases, right? So we also have this other potential advantage here, which is that we can be as at millimeter wave, what we typically try to do, as you will see, is that we operate directional links where the THs and RHs are operating in a focused manner to each other. So as a result, what we see is the interference to other users can be reduced, right, through directional links. And we will see how to build these kinds of directional links at millimeter wave, right? And all of this has led to a lot of interest in millimeter wave and deployments, right? So there are already existing standards which are FR2 for cellular slash for networks, and then there is the 802.11 AD and AY, right? So this basically are the next generation, are the Wi-Fi networks operating at 60 gigahertz, right? And if we look now, we also see that people are actually trying to build communication links at even frequencies greater than 100 gigahertz for D-band point-to-point links. So from a communication perspective, the advantages are clear, right? So you have higher data rate, smaller size, and potentially lower interference. Okay, but there are of course challenges with operating at millimeter wave, which we will discuss shortly. So this is from a communication perspective, right? Now let's actually evaluate things from a radar perspective. So in general, let's say that I'm trying to image a system, right? So I typically, let's say that I have, we'll see how to do it now, but let's say that I have multiple antennas in my system somehow, right? And I'm trying to image an object, right? And I'm interested in finding out, so there is a wave that I send and there is a reflected wave that comes back, right? And I'm trying to detect the shape of the object or some features using this. So the resolutions that I care about, let's say in this dimension, let's say that I care about the delta H resolution that I can resolve. And in this dimension, let's say that I want to resolve a certain range, right? And let's say that this object is moving, right? If object is moving, I want to know the velocity, right? So measure velocity with resolution of delta V. Yeah, so in this scenario, what we notice is that, or what we can basically show is that the delta H resolution that I have, right, that is proportional to the wavelength divided by D, where D is the size of my measuring aperture. So if I am able to measure delta H, delta Y, delta Z and the moving object with velocity resolution delta V, I can really image the world that I am seeing. So here we see that delta X is proportional to lambda over dx, which is your aperture size in the X dimension, right? And if you made a 2D antenna array, right, where this side you again had antennas with dy, then your delta y would also be proportional to lambda over dy, right? So this is already one motivation. So this basically implies for same aperture size, right? So let's say you're limited by the physical size of your system. Your car bumper is only so much, has only so much size, or your automatic or your robot has only this much width and breadth, width and length. So for the aperture size, if you basically reduce lambda, this would imply that your delta X and your delta Y reduce, right? So that's desirable. Okay. So that's the first step. Now imagine that the object is a certain range r away from the radar transmitter, right? So the total distance that the signal has to travel and come back is 2r. The time that it takes to travel that certain range is 2r divided by c, where c is the velocity of light, right? And if you are basically, the way that this is working is that at, so let's say this is t, right? You are sending a pulse, right? And this pulse is traveling and then is getting reflected and comes back, right? After a time that is 2r divided by c, right? Then your ability to distinguish between multiple objects depends upon the ability to be able to see pulses that are, let's say, a certain delta t apart, right? And this depends, of course, on what is the duration of your pulse, right? And what we can basically show is that the delta t basically depends upon the pulse duration. The pulse duration is 1 over the bandwidth of the system, right? So basically what we see is this is 1 over the bandwidth of the system. So this basically implies that that your range resolution, which is delta r or delta z, right, is c over 2 times the bandwidth. So this implies that increase bandwidth to improve range resolution. Right? So what we see is that if we reduce wavelength, we will get better XY or what we call azimuth elevation resolution. And if we increase bandwidth, we will get better range resolution. And finally, we won't do the whole derivation here, but you can show basically that when an object is traveling with a velocity Vr, right, the way that you measure it is by measuring the Doppler shift, right. So the Doppler shift that you see, which is the way that you measure the velocity, right. The Doppler shift that you see is 2 Vr divided by lambda. So then this basically says that in order to get a certain velocity resolution delta Vr, right, you can basically show that that is lambda over 2 times what we call Tc, or basically this is the observation time, right. I'll just talk about the intuition behind this. I'm trying to measure a shift in this frequency, right. So I'm trying to either measure Fd or Fd plus some delta Fd, right. I'm trying to determine that in order to determine a velocity change. But in order to measure something in frequency domain that is of the order of a delta F, I need to observe the signal for 1 over delta Fd, right. I need to observe it for that long in order to be able to determine that the frequency has changed. So this we basically call Tc, right. So what you can essentially see is that delta Fd is 1 over Tc, so delta Vr is lambda over 2c. But the key takeaway here is also, again, if you want to measure with good velocity resolution, you want to lower your wavelength and increase your Tc, or the time for which you observe your signal. So coming to, so the conclusion is that from a radar perspective, right, from a radar perspective, increasing the frequency of operation decreases lambda, right. This in turn improves delta x, delta y, and the delta v, which is the velocity resolution. And this also increases the bandwidth, so this improves range resolution. Right? So there is a lot of motivation then to do this at higher frequencies, right? So if we look at these systems, then people started doing radar at around 24 gigahertz, and now your automotive radar, right, is occurring at 77 gigahertz, right? And people are trying to build radar at 94 gigahertz and 140 gigahertz, right? So people are trying to continually increase the center frequency of operation to derive these benefits, right? So overall, from a radar perspective as well, I would like to move to as high a frequency as possible. So just to give you a sense from a system perspective, right? What I have included here is what the Telecommunication Union has recommendations for radar systems, right? And what you can see here is that depending upon the application, the specifications are sort of changing, but overall this is all targeted for automotive radar that is operating in the 77 to 81 gigahertz band, which is agreed upon by everybody. And you have applications where the radar is looking in front in order to enable cruise control, or the radar is trying to do very short range applications in order to help the car park and things like that, right? So the ranges are dropping, and we will talk about this particular spec in a little bit. But what we effectively see here is that the transmit powers that are needed going to the antenna are considered to be of the order of 10 dBm, right, or 10 milliwatts. And the bandwidth that we are operating with ranges from 1 gigahertz for the collision avoid cruise control, automated cruise control applications, to 4 gigahertz when you are really wanting high resolution in order to do automated self-driving and automated driving and things like self-driving cars and things like that. So the kind of resolutions that people are targeting are of the order of sub 10 centimeters. But even this is not completely enough, right? So in order to truly enable these applications, there is motivation to push this to even higher frequencies, like I said, 140 or even all the way up to several hundred gigahertz. There is also, from an application perspective, you can't just transmit and only worry about yourself. You have to worry about the interference that you're causing, for example, to other automotive radars that are operating. So there are limitations on unwanted emissions. There is also here, we will talk about this as we keep going forward, receiver performance limits. So how sensitive should the receiver be? What should the receiver noise figure be? What should the receiver linearity be? So there are all these specifications as well that people work with. So broadly in the systems and the radios that we will be talking about, we are trying to meet these type of specifications that are being provided by the at the system level for radar and for communication, right? So hopefully this gave you a summary of the kind of applications that are there, and I've put down a list here in the notes for future reference. But you can see that across millimeter wave itself, it's beginning to look a little bit like what we showed in the spectrum below 6 gigahertz. You can start seeing that there are many applications that are coming up. The big ones are the 5G in the 24 to 30. There is the 60 gigahertz Wi-Fi. There is the backhaul, and there is the radar, right? So you can see that there is a mix of applications in terms of different communication applications as well as radar applications that people are operating over here. Again, something in the literature to consider is that these bands people have been working in historically for different applications. So they have what are called letter designations and also waveguide designations. This is again just a nice to know, but many times people will be talking about K-band systems that are being used in satellite, or which include Ku and Ka bands operating in the 12 gigahertz and 26 gigahertz. And the 60 gigahertz ranges are referred to as the V band, with W band going above it. So these letter designations are based on are done for historical reasons. And the other thing to note here is from a measurement perspective or equipment perspective, many times we use waveguides at these applications. So these bands will also be referred to as WR with two numbers after it to designate what band that is. So the trick is that in the waveguide, there is a certain width here, right? And this width in mils, which is 1,000th of an inch, right, is this number over here, okay? So basically what happens is, as you get to higher and higher frequencies, this width of the waveguide is reducing, right? And as a result, you can see that the numbers are coming down as we are going up in frequency. Again, this is just a nice to know, because when people are talking about systems, they will often use this band designations. Less the waveguide now, but at one point of time. From an equipment perspective, though, it's important to know which waveguide system is used to measure which band. So that's useful. So hopefully this gave you a very high level overview of why we want to do millimeter wave in terms of range, resolution, and data rates of wireless systems. Any questions before we move to the next topic, where we'll discuss the kind of transistors and passives that we have to build systems at these frequencies? Okay, so let's talk about the technology itself that we operate in over here, right? So there are many transistors. So we'll begin first with transistor technologies, right? Right. There are silicon-based technologies. So you have CMOS transistors, and then you have BJT, right, which is basically CD BJTs. So this is one set of technologies. And then we have the 3-5 technologies, where we have gallium arsenide, gallium nitride, indium phosphide, right? So you have transistors that are made in these materials as well. We will discuss these in just a broad overview, or whenever we are talking about silicon, we'll sort of compare them to these technologies. But this typically have very high performance, right? High power, low noise, particularly gallium nitride and indium phosphide, right? But they have high cost, right? And integration level is low. So we focus on CMOS and bipolar or CD technologies in this course, right? And these can be potentially low cost, but in volume. So you need to make millions of devices to realize a low cost, because the initial mask cost can be high, right? And they have limited performance, particularly at high frequencies. And we'll see that in a second. But this is improving, right? And over the last 2 decades, as technology has scaled, right? So this improves with technology scaling. So so we have these CMOS and BJT technologies, right? And in CMOS itself, right, we have 2 flavors. We have the bulk CMOS, right? And in bulk CMOS, basically you have the source, you have the drain, and then the gate. Right? And then you have the substrate. And we have what we call the fully depleted FD silicon on insulator technologies. Right? And what are these fully depleted technologies doing? They basically, you have your source, you have your drain, right? and right over here you have a thin buried oxide layer, a box layer, right, which is an insulator, and below that you have your silicon substrate, right. And since this silicon substrate is now not constrained in doping by what you need from the transistor performance, this can be high resistivity silicon substrate. And then of course you have your gate as usual. And the advantage of this technology is that here you have all these capacitances that are going to the bulk, right? And here those capacitances don't exist because these are this buried oxide basically isolates the silicon from the source and drain. So as a result, this technology has much lower parasitic capacitances, right? Lower parasitic capacitances. Right? And therefore higher frequency of operation. It also has some advantages related to leakage for digital technologies, right? But I mean, that doesn't concern us so much as millimeter wave designers. It also has some advantages related to breakdown voltages, and we will talk about those when we are talking about power amplifiers, about how SOI technologies enable us to do different power amplifier topologies. So that was CMOS, right? And then we also have the BJT technologies, right? And the reason why I'm sort of highlighting the way that the transistor physically looks is that it's important to know that, because at millimeter wave, you don't use a lot of devices, but what you want to do is completely understand each device's layout and performance, and understand the choices that you are making in layout, how they impact the device's performance, right? So in silicon, in bipolar, you typically have the emitter, right? And then you could have a base connection coming in from one side or two sides, right? But generally you have the base over here, right? And that is connected out. You could have a connection on the right as well to make it a symmetric thing. And then below that you'd have the collector over here. Right? So the important thing to see here is that BJT is a vertical device, right? And the CMOS PET is a lateral device, right? And what we typically see is that we can actually here see some figures of merit for the different technologies here, and some of these are expected, some of these are sort of real, right? But the important thing to note here is that if we look at and we will talk about these performance metrics, right, FT and FMATs. For now, let's consider them as FOM, figures of merit that indicate high frequency performance, right? So we'll talk about how these are good metrics to determine which technology, how much gain you can get out of technology, right? So that's what these metrics are providing. But what we can see is that firstly, when we look at the heterojunction bipolar devices, they for a smaller feature size, they achieve the same sort of performance, for a larger feature size, they achieve the same sort of performance compared to a MOSFET. So you don't have to scale the BJT as much as a MOSFET, right? But with MOSFETs, the advantages that you have is that all the technology development for MOSFET commercially is happening for digital systems, and millimeter wave circuits are just piggybacking onto that. So in net effect, it is, if you are able to build it in volume, the CMOS circuits can be lower cost than the BJT. But in terms of raw performance, usually the HBT devices, the heterojunction bipolar devices, do better than the CMOS devices, definitely at comparable feature nodes, and then even at a couple of generations behind in terms of the feature size, the HBT technology does quite well. One key takeaway here, of course, is that from a figure of merit perspective, what we see is that with FD and FMATs, we now can easily access commercially devices that are operating with FD FMATs greater than 250 gigahertz, right? And some of these numbers, it depends upon how many metals you have connected or where the, you're counting the plane of the device to be. But still, even if you consider practical devices laid out in a practical way, you can get FD and FMATs in the 200 gigahertz range now. And with that, you can build useful circuits at millimeter wave frequencies in the 30 to 100 gigahertz range. And these are commercial technologies. So if the application demands large volume of ICs, then we can have the same sort of revolution in millimeter wave technologies that we had in Wi-Fi and cellular once we moved those systems to CMOS. So if millimeter wave systems work in CMOS and by CMOS, they can potentially access pretty low cost as well. So while we are doing this scaling, what is the cost of this? Well, it turns out that there is a material limit which is called the Johnson limit, and we will again talk more about this in the module on transistors. But effectively what we see is that if I multiply Ft by the breakdown voltage, right, that is effectively a material property, right? Now I want high Ft to operate at millimeter wave. And I achieve this usually, for example, in CMOS through reducing L in CMOS, right? And when I reduce L, also I reduce the thickness of the oxide. This implies that I reduce the breakdown voltage, right? So you can see intuitively that there is a trade-off between Ft and breakdown voltage, or Ft times breakdown voltage is a material property. And shown here is the breakdown voltage plotted against Ft for different families of devices. And what you can basically see over here is that some of the other technologies that I mentioned, for example, gallium nitride or indium phosphide, they have a much better figure of merit here. So for the same Ft, they have a much higher breakdown voltage. And if they have a higher breakdown voltage, typically what that means is that they can generate more output power, right? So what we find is that by being in CMOS and CD by CMOS or CD HBT, what we are doing is we are limiting the amount of power that our devices can generate at high frequencies when we get high Ft from them. And this trade-off we will see now some more in terms of link budget, right? So from a technology perspective then, while we have devices that can operate in small signal at high frequencies, they don't operate very well in large signal at high frequencies just because of this trade-off that I have. Which is why if you look at research right now, for example, you'll see a lot of gallium nitride hemp devices being used in power amplifiers, because you can get really high output powers from these devices even at millimeter wave frequencies. What are the other parts that we need in order to build the circuits, right? So we need these devices. We see that FTF mats, which is that figure of merit, is getting high. But what about the other inductors, capacitors, all those other things that we need to build circuits? So we typically build those circuits using the metallization that is there in what we call the BEOL, or the back end of the line. And this is a place where silicon shines, because silicon has a pretty complex back end of the line that supports many metal layers, right? And using these, I can have quite complex interconnect, right? And this enables me to achieve very high levels of integration, right? The next advantage in CMOS is that this interconnect has very fine resolution, right? And this basically means that devices and circuits, devices and circuit passives, right, can be close to each other. So this lets me build circuits in a different way than conventionally in gallium arsenide or 3-5 technologies with more limited metal layers. And finally, in response to the push towards integrating RF and millimeter wave circuits in CMOS and CG, what's happened is that the back end of the line has started supporting thicker metal options, right, for the last metal. So for example, here you can see that the top 3 metal layers are somewhat thicker than these lower metal layers, which are designed for basically digital routing, right? But using these, I can build inductors and capacitors, and as we will shortly see, transmission lines. Okay. And also, while this is not a feature of every CMOS technology, it is possible for some of these technologies to have high resistivity substrates. Right? And these basically reduce loss in the passives. Right? So with this combination of devices and fairly complex back end of the line, I can now come up with quite creative circuits. I can extend the kind of things that we do in analog frequencies or RF frequencies out to millimeter wave. So one question that we always grapple with when we start designing at high frequencies is this concept of lumped versus distributed systems. Right? And it's useful to talk about this when we are discussing this complex back end of the line, because for example, in CMOS, I might have a device, right, which has a gate connection over here, right, and then I might just be able to build a set of VRs, and then from these VRs, I'm going out to an inductor, right here. So these distances over here can be of the order of 10 microns, right? And this inductor itself can be of the order of 100 microns, right? So I can build pretty fine structures. So now the question is, what do I, how do I model, or how do I design, or how do I think about millimeter wave design, particularly integrated design? So here we have to ask, okay, when we do lumped and distributed systems, what do we mean, right? So overall, when we talk about KCL or KVL, right? So let's consider two nodes, right? And there is a load here, there is some impedance ZL that is connected to this node, right? And there is a wire that is connecting, and I'm just going to represent the wire like this, right? That is connecting these 2 points. Let's call this node A and let's call this node B, right? Then if we think about KCL or KVL in our analog domain, we say, okay, these two nodes are connected together, so they are the same node, right? And so I can say that VA equal to VB is some, let's call this IL, that's IL times ZL, right? I can just directly say that. But this is an approximation, right? So what is the approximation I'm making? I'm approximating that if I apply a signal here that is VA, the signal at VB will be exactly the same, right? But now let's imagine that there is some delay that is there, tau, between them, right? So in reality, then what will happen is that this signal over here is actually a delayed version of this, right? So now so if I think about at any given instant of time, right? So if this is time over here, right? These two voltages are not the same. This is here, and in that instant, this B is over here, right? So if I were to apply my traditional KVL equation, I should say that there will be a current that will flow, which will depend upon VA minus VB, right? So what is my lumped approximation? My lumped approximation is basically that tau is 0, or I'm saying that the velocity of light or the velocity of the EM wave is infinity, right? That is basically the approximation that we always make when we are doing lump circuit design. But there isn't anything magical here, right? If we want to build a better model, and this is an engineering approximation. So if I want to build a better model, I say, okay, you know what I'll do is I'll split this distance between A and B, right, into several sections, right? Let's say I put it into 3 sections, and let's call this H1, H2, right? So then what I try to do is I say, okay, I'll model the relationship between VA and VH1 in some way, H1 and H2 in some way, and H2 and B in some way, so that eventually what is my interest? My interest is that I am able to predict the current that flows here. I'm able to predict VA and VB, right? I want to be able to predict it. So in order to do that, for example, typically in order to build a delay model, right, we consider RC to be a delay cell, right? So I might say that in between each of these sections, right, this is node A, this is node X1, I'll place an RC, I'll place another R and C, right, and I'll place another R and C. And this might be a good way for me to model what happens from VA to VB. Correct? So I have begun the journey towards distributed systems, right? Because I'm modeling the interconnect through a multi-section model of some sort, right? But if I were to think between VA and H1, I do have what I call a lump circuit. I do have a resistor. But what I'm basically trying to again do is I'm trying to approximate a smaller and smaller tau as 0, right? And now logically, this also says that there is a frequency relationship here, right? Because clearly, if I have a situation where there is a tau that I am approximating to 0, right? And this tau is a significant, let's say that the time of the time period of the wave that I have is 1 over f naught t naught, right? If tau by t naught is significant, right, then I am making a bad approximation, because then if my wave my VA looks like this, right, and my VB, which is shifted by tau, is significantly shifted in phase. However, if it turns out that compared to a time period this shift is very small, then what I would see is that the shift would be very close, right? And so my approximation would still be valid. I can now assume that VA equal to VB. So then what we see is that this approximation doesn't depend purely on tau. It depends upon tau as a fraction of T naught, or to put it another way, it depends upon from VA to VB, from node A to B, whatever length I have, right, this length, what is the fraction of wavelength that it is, right? And typically we say, for example, we say if it is 10%, then you can, live in the lumped world, right? And if it is greater than 10%, right, you have to build a distributed model, right? But effectively, I mean, rather than think in terms of these rules of thumb, we can think rather in terms of, okay, how accurately do I want to predict my VA to VB, right? And so I need to put enough sections in there so that I'm accurately modeling what happens. So now I can model these, continuing on the lumped versus distributed discussion, right? So what I can do is I can see that there are situations where when I have R and C as my model for my multiple sections, even that isn't enough, because this predicts a low pass response, right? And that may be not what is happening at the frequency that I have. So then I move to a model where I start modeling the interconnect in terms of sections of LRGC, right? Some L of the unit section, some R in the unit section, some G of the unit section, and C of the unit section, right? And I repeat this again and again, right, to get from A to B, right? And how many sections should I put? Well, again, depends upon how accurately I want to do this, right? But if I really want to be super accurate in the continuum, what I find is that the distributed model that I have is basically the model of a transmission line, right? So I can start modeling the interconnect between A and B through through these LURU infinite sections, or very small sections of them, right? So then I'm sure you've studied this, but I just wanted to do this from this perspective, that you can say that you have a transmission line of a certain impedance Z0 and a certain length L, right? And then you can predict VA to VB accurately, right? Because we know how to model what happens with this transmission line. So we will be doing that shortly. So when we do this though, we have to ask ourselves, okay, in the integrated circuit domain, which world are we living in, right? So if we go back to my example earlier, if this is my transistor, this is my gate connection, and I have some VR that is going up, and then I have an inductor that is running over here, right? Okay, that was undesirable. Yeah. Then I basically am operating in something that is of the order of tens of microns, and this is something that is of the order of hundreds of microns, right? So if we consider, let's say, 60 gigahertz, right? At 60 gigahertz, the lambda in air is 3E8 over 60E9, so that is 5 millimeters, right? And if I consider just silicon dioxide, right, the epsilon of silicon dioxide is 4, right? So then the lambda in the silicon dioxide is approximately 2.5 millimeters, right? So now if I consider lambda over 10, that is 250 microns, lambda over 20 is 125 microns, right? So that means that if I were to just model this distance, I can probably do this maybe using R's and some small L's and some C's or something like that. But over here, I might need multiple sections of the models. Maybe this, trying to model this as a single inductor will not work, right? Maybe I need to model it with something more complex. Maybe I need to have multiple inductors and multiple capacitors to model the system, right? And so that's why we basically in millimeter wave IC design on chip, we have to be able to move between these lumped and distributed worlds. So we will have resistors, capacitors, inductors, as well as transmission lines on our chip. And this is just as an example, let's say that this is its drain, right? And somehow next the drain of that transistor is going to the gate of another transistor, okay? So from a circuit model perspective, right, you might have something that looks like this, right? I mean, I'm sure you need to have capacitors to break it all up, but let's assume all that exists, right? All that infrastructure exists. But now this model over here, if I model it with a single inductor here, this may not be accurate because the dimensions of what I am trying to model are of the order of lambda over 10, lambda over 20 in that range. So then what you need to start doing is think about the model for this component, right, in a more distributed way. So then maybe what you end up with is a model where you split this inductor into two inductors, right? And you model each of those inductors with L's and C's and R's, right? And that gives you a more accurate model because of the delay that is involved, right? So, so every time, what are we trying to do? We are trying to make sure that we can model the voltage here and the voltage here, right? And our observation is that when A and B are separated by a long distance, right, what we see is that if this is some I over here, right, and if I look in here and I see a ZL, which is VB over IL, what I see looking into A is not equal to ZL. I see something else if this distance is long, right? And why do I see that? Well, because of that effect that I said, right? Here the voltage is a certain voltage and the current is a certain current, but here the delay has to be accommodated for at BA, right? So we need to model what is happening in the interconnect more accurately in order to be able to predict what the voltage relationship is between here and here. Does that make sense? Yeah. And this goes both ways. So it isn't always true that you have a distributed system, right? Maybe you have a transmission line and you approximate it with a lumped system, right? You might have a situation where you build LC sections for your interconnect, right? But in order to approximate it, you say that, okay, this is actually like a transmission line where the impedance is some Z0, which is square root of LC, and it has a certain electrical length that depends upon square root LC and the number of sections that you have, right? So you can go both ways. You can take a series of lumped circuits and approximate it with a distributed system, and you can take a distributed system, approximate it with a lumped system. But in the millimeter wave IC space, that is the one key challenge, which is an engineering challenge, which is to know when should I model an interconnect with inductors, capacitors, when should I model it with a transmission line, when should I model it with just an RC, I don't need to worry about these kind of distributed effects. So that is the intuition that you build in your design process, right? So, but the takeaways from here is that the transistors are good, the back end is good, and if we are able to build lumped and distributed models, right, needed for millimeter wave design, right? But once we are able to navigate that world, we have everything we need to be able to build circuits in silicon. So we can basically build both with the existing backend, we can both build inductors, capacitors, as well as distributed components like transmission lines. So just as an example, you can build a microstrip transmission line, right? So this can be the top metal layer, right? And this can be a lower metal layer for ground, right? So this is the ground, this is the signal, right? And together here, this is SiO2 in the middle, right? And you basically have a microstrip transmission line here.
Sorry, sir, again.
Yeah. So this spacing is usually of the order of 10 microns, right? In that range. So there are several kinds of transmission lines that you can build, right? So let's focus on this microstrip here, right? So from a design perspective, let's say that you have 7 metal layers as an example, okay? 7 metal layers, right? And so what you would, and let's number them M1 through M7, okay? So what you would do is in M7, you have your signal trace, okay? And then in M2, you have a ground plane, right? So this is in M2, right? And you have, you have the substrate below it. This is H, right, in microstrip terminology. And then below this, you have your silicon substrate. But the silicon substrate, right, you don't want your signal to actually leak into it. So what you have is this W of your ground, right, is actually W of the ground is much greater than the W of your signal, right, to make sure that all your field lines are ending here. So you don't have this concept of leaking into the substrate, but it can happen with microstrip that this occurs because, you know, you don't want, if you keep trying to make WG very large, you do run into this difficulty that your circuits become just very large, right?
Yeah, but in microstrip, generally the ground plane has to be uniform and very large.
Infinite, right? That's basically the assumption. You find that if you are something of the order of 5 to 10 H, right, in this dimension, it's fine. It's fine. You can work with it. And then I'll show some layouts where what you end up doing in your circuit is that you end up making your, that also, but your circuit itself, your IC, might look like a giant M2 ground plane with holes in it where your devices are.
Defected.
Yeah, exactly. So your devices are here. Let's say this is another device over here, right? And then what you want to do is you want to build a microstrip now, right? Let's draw that microstrip in orange. This microstrip runs over here, right, between these two devices. So the ground underneath the microstrip is quite wide, right? And it isn't that you are breaking up in area, but the challenge might be that you want to have another microstrip that is running here, right? And there might be some other component over here, right? Let me keep my color consistent. So you might have another device. You might have another device over here, right? And with this device, right, you have another connection coming, right, let's say. Now the problem is that you need to have enough spacing between these two microstrip lines in order to make sure that they don't couple with each other. So it becomes a question of designing a planar IC, but this is actually how MMICs are designed. And you can do the same approach in silicon. But you can go one better in silicon, because what you can do is that you have access to very high resolution vias, right? So what we typically end up using in silicon is a structure that looks like this, which is we have a ground, we have a signal, we have a ground, and then so let's say that this is all in the top metal layer. This is all in the same analogy that we were using. Let's say this is all in M7, and then you would have some vias, and these vias go down to your lower ground plane in M2. So this is M2. So you can have basically periodic vias, right? So with this approach, you're effectively, if I look at it from the top, I'll have basically my signal line, my ground line, and then I will have vias or what we call a via wall, right? And this via wall is going down to my M2 ground underneath. Right? So with this structure, I mean, and this dimension can be totally, in order to get 50 ohm, you can accomplish this in about a width of 50 microns. So now you have a very compact transmission line structure which doesn't see silicon at all, right? In practice, in theory. In practice, what happens, again, we are getting into detail, but that's fine. The practice, what happens is that you cannot have such a wide ground plane because that violates density rules. So what you end up having to do is to mate strips of it, right? So you end up having to mate strips here of M2, right? So these are strips of M2. They can't, so there are gaps, right? But what you can do is, imagine that there is another layer that is M1 below, and that M1 you can make it overlap in these regions, right? So that's M1 ground. So looking at it on the 3D view, then basically what you also have is another via going down, and you have a M1 ground also on top of this, right? And once you do this, you are pretty well isolated from the substrate. And we will just see the kind of losses that people see, right? But you can build these kind of distributed structures in silicon pretty accurately.
Losses will be more compared to MMIC because there the ground plane is more uniform?
I think the losses are worse in MMIC because this is copper and not gold. So in MMICs, quite often they use gold interconnect, which has better conductivity than copper. So that is one. I think it is true that they use high resistivity substrates there, but I don't think it is necessarily, not a lot of signal goes into the substrate in this. If you were to run an EM simulation and look at it, you don't see that much substrate once you do this kind of shielding with multiple metal layers one below the other. Most of the losses, additional losses you're seeing are simply because the metal film is not as thick, and the metal film is gold and not copper. And okay, actually I should add one more note. It is that in while technically this is all empty, in reality you have to put other metal layers in here because you need to meet metal fill. Because in silicon you cannot leave any region of metal empty for a lot of area, so you have rules that say that there should be a minimum density, right, to meet minimum density. So this becomes a problem, right, and you see higher losses because of that. Now everybody is aware of this, and now foundries will offer you an option where you can designate some areas of your chip as what are called low density areas, and as long as you don't have a lot of them, the foundry will let you get away with low density in those areas so you can reduce losses. Yeah, so in practice over here you can see examples of a couple of backends where you have thick copper and thick aluminum at the top, right, and you can do your ground, so shown here are some examples of metal stats. Usually in order to attach to bond pads, the last layer can be aluminum, right? And with these you can build transmission lines. Just as an example here, again, to set, I found this data that I found in this paper quite useful, right? It basically tells you the kind of losses that you would expect to see and the kind of lambda wavelength that you expect to see in silicon. So you can see that basically at 60 gigahertz, thinking that you'd be at a dB per millimeter loss of routing is a very reasonable estimate, and you should be able to get that, right? And yeah, I mean the phase is yeah, I mean I think this 140 to 160 degrees per millimeter is generally a good estimate at 60 gigahertz. Again, it depends upon the frequency, but there is also a limitation on. We'll talk more about this, but there's also a limitation on how high and low impedance you can go, right, depending upon the width and the spacing and things like that. But overall, very feasible to do millimeter wave interconnect with 1 dB per millimeter loss or less than that on transmission lines on the chip. And you can see also what I mentioned about the metal fill here. So if you have this structure that we just discussed, and then you put the metal fill in all the other layers below, and this is a lower density metal fill, right? And what you can see is that it makes a big difference in terms of the loss that you get by reducing metal fill, particularly at high frequencies, because then there are all these eddy currents that get set up in these metals that cause problems. So now that we have seen that we can basically build devices, passives, and transmission lines, what are the kind of performance that people are getting at millimeter wave in these technologies, right? So if we will, for those unfamiliar with noise figure, we will introduce that when we are talking about receivers and LNAs. But consider this as a figure of merit for the noise that the receiver is adding to the signal, or how much it is degrading the SNR. But what we see is that basically 2 to 5 dB noise figures are possible at millimeter wave frequencies, right? So there is a sort of technically proportional to frequency here if you consider only the devices. But in reality, the noise figure is impacted by not just the devices, it's also impacted by the L's and the C's in the transmission lines, right? So it doesn't quite follow that. But overall, we can see that these kinds of noise figures are feasible. And if we look in terms of output power, we see that basically there is it's feasible to get 10 to 20 dBm per PA. In fact, people have demonstrated 23 dBm, 26 dBm numbers like that. So to translate that, this is 100 milliwatts, right? And 30 dBm is 1 watt, right? So 1 watt is kind of challenging. 100 milliwatts to 200, 400 milliwatts people have demonstrated. That's feasible. But there is a question of area as well, and we'll come back to that. But these are the sort of numbers that we can expect to get in silicon now, right, at millimeter wave frequencies. And you can see that there is a broad range of possibilities here. So given these kind of metrics, which is 2 to 5 dB noise figure, 10 dBm to 20 dBm output power, right, what kind of systems can be built? We saw that if we look at that radar that we discussed, the ITUR recommendations, they said 10 dBm output power, right? So it looks like from a TH perspective for radar and RH perspective for radar, we are well within feasible territory, right? But what about communication, right? So let's just work through a sample link budget, right? So if we consider let's say that we are considering a modulation format where we want the receiver output SNR, right? We need 20 dB output SNR over here. That's our objective, right? And in that scenario, the way that we model our receiver is that we consider that the receiver at its output, right, it degrades whatever the input SNR was by a factor f, which we call the noise factor, right? So the SNR out is SNR in divided by f, right? So this implies that if I need a certain minimum output SNR, my SNR min is f times my SNR out, right? So if that is true, then I see that I need f times my SNR out as my SNR min, but SNR itself is signal to noise, right? So this is the PRX min divided by the noise, N in, input noise, right? This must be f times SNR out. And the input noise that I have is KT times the bandwidth that I have in my system, right? That is my input noise. So this basically implies that the minimum received signal that I need is f times SNR out times KT times bandwidth, right? This is the minimum received signal that I need to have in order to make sure that my output SNR matches what I want it to be, right? And here, this is a multiplication, so in log domain, everything adds up, right? So I need 20 dB SNR, right? KT is Boltzmann constant times 298K, so that is minus 174 dBm per hertz, right? 10 log bandwidth, let's say that my bandwidth is 1 gigahertz, right? So this is 90 dB for 1 gigahertz, right? And let's say that my, I think I made an assumption of f in my example of 7 dB, okay? So let's say that my f is 7 dB, right? So this tells me what is the minimum received signal that I need to have in my system. And we can work through that math over here, right? And what we end up with is that the minimum input power that I need is minus 57 dBm, right? With the following assumptions that my bandwidth is 1 gigahertz, my noise factor, noise figure or 10 log f is 7 dB, right? And I want 20 dB SNR at my output. So making these assumptions, I see that my noise floor is minus 77, SNR of 20 dB. So my input power that I need is minus 57 dBm. So the transmitter must now push out enough power, right? So that at the input, I'm able to receive minus 57 dBm. So how much power does my transmitter need to generate? So when we asked ourselves that question, we have to figure out the transfer function between the transmitter and the receiver, right? And for that, we have this equation which we call path loss, right? And path loss is 20 log lambda over 4 pi d, right? Now this path loss is an ill-named thing, right? Because it's not really loss of any sort, right? What is happening is that I have my transmitter, right? And my transmitter is radiating in all directions, right? It is sending power in all directions. And my receiver is only picking up a fraction of this power, right? This is the, let's say, the area of my receiver. So you can see clearly that the PTX, if I divide that by the area of the sphere, right, which is basically the distance between the transmitter and the receiver, that times area of the RX will be my PRX, right? The area of the RX itself, I can show that it is proportional to lambda squared, right? So that is where this equation for path loss comes from, that you have 20 log lambda divided by 4 pi d in the dB domain, right? So if we consider this path loss, right, so let's get one metric of just this path loss alone before we, one slide over, right. So if we consider this metric of path loss alone, so for example, this is at 20, these plots are at 28 gigahertz and 60 gigahertz, right. And what you see here is that at 50 meters at 28 gigahertz, this 20 log lambda over 4 pi d is minus 95 dB. Clearly, if you go to higher frequencies, so this is 20 log lambda over 4 pi d, right? As you go to higher frequencies, lambda is falling, so this number should become more negative, right? And so you see that if I was operating at 60 gigahertz, then I would see something that was in the minus 102 dB range in terms of path loss. But at 28 gig, it's minus 95 dB. So if I then say that, okay, my TX should then be able to accommodate for this path loss, I'm basically asking my TX to generate minus 57 plus 95. So I'm asking my TX to generate 38 dBm of output power. So 38 dBm of output power translates to 6.3 watts. If I'm assuming 10% efficiency in my transmitter, that is 63 watts of DC power. So this is not a feasible integrated system, right? And this is already a pretty optimistic assumption, because all I've considered here is this idealistic path loss, or basically the fraction of the power that is lost in the fact that the TX is radiating everywhere and I'm just capturing some part of it. But in reality, there is also what we could call the propagation loss, right? Which actually is loss that the signal sees going through air, right? And what we see, people have carried out measurements on this, right? And what we see is that if we look at millimeter wave frequencies, there are the attenuation or the propagation loss that we see in terms of dB per kilometer stays pretty small. So for example, at the 28 gig that we considered, right? So I believe these are numbers that are at ocean level and higher altitude, right? So what you basically see is that even as you grow across to ocean level with more humidity and everything, you basically are only dealing with something that is of the order of a dB per kilometer, right? So we were considering 50 meters. So this is not really going to be a problem. But there are some frequencies where there are some material absorption bands. So for example, there is an oxygen absorption band at 60 gigahertz. So here, for example, very specifically, if I go at 60 gigahertz, I can get even losses that are of the order of 10 dB per kilometer at these frequencies, right? And in the spirit of innovation and entrepreneurship, we change this from being a bug to a feature, and we say, no, now I can build very secure links because somebody far away cannot detect a 60 gigahertz signal. So I can actually build short range links that are more secure at these frequencies. So those kind of arguments are made, right? But actually what really impacts the situation here is not attenuation through air when there is no rain, but what really kills millimeter wave signals is rain and fog, right? So if you are building an outdoor millimeter wave link, right, and when it is operating in rain, you can get losses. So the losses can be of the order of 30 dB per kilometer, right? So you get basically 10 to 30 dB per kilometer attenuation at frequencies greater than 50 gigahertz, right, in rain. So then if you're trying to think about the system that we just said, we said 38 dBm was high, right? But now if we have to accommodate another 10 dB, right, that's 10x the power. So we have gone from 6.3 watts to 63 watt output power levels. So this makes point-to-point backhaul links at millimeter wave quite challenging to build, right? Because they have to operate in with low error. And fog also doesn't help, right? So fog, you can show that it's about 2.5 dB per kilometer at 50 gigahertz, right? And it goes to about 5 dB per kilometer at 100 gigahertz. So these are real propagation losses, right? This is nothing to do with the fact that the TH is radiating everywhere and things like that. So this, from a system link budget, if you're building outdoor links, you have to always consider. So coming back to our problem, right? We see that even if we ignore all these propagation losses, we basically are demanding a lot of power from our transmitter. But we also see that that is simply because we are wasting the TH's power by radiating it everywhere. So we should not radiate the power everywhere. Instead, we should be more like a flashlight as opposed to a bulb, right? So we should try to basically make the TH radiate more of its power only towards the receiver, right? And this can be done, and the way that we do it is through directional antennas, or the concept of what we call antenna gain, which is basically the antenna focusing the power in the transmitter. And similarly, the receiver being more sensitive in the direction towards the antennas and collecting power in that from that direction, right? So we can basically first begin by saying that I will have 15 dB of antenna gain, which effectively then takes my minimum TH power down to 23 dBm, right? And now my system power is 2 watts. So this is beginning to already start look quite reasonable. I can imagine building such links provided I didn't have to deal with all those other propagation losses. And then I can say that I will add gain on the antenna side as well, right? And then if I add gain on the antenna side and on the receiver side as well, so if I add gain on the transmitter and the receiver side, now I see that the transmit power that I need on average is about 8 dBm, and I can basically start building links which are integrated, right? But I still haven't solved the problem of building those high gain antennas. But if I could build those, and we do know how to build high gain antennas that are directional, we can build waveguide antennas that form point-to-point links. But the problem is that there is a fundamental relationship between the gain of the antenna and the beam width of the antenna, right? So the gain of the antenna is related, so it's related basically to the area of the antenna, right? So firstly, if I want to have high gain, that implies that I have to have high area in my antenna. So that's the first thing, right? And the next thing is that when I increase the gain of my antenna, I basically end up reducing the beam width of my antenna. I should call it BW since we've been using that for bandwidth. So let's call that beam width, right? So there is the beam width of the antennas. So what we see that if we have 20 dB antenna gain, that's about 20-degree beam width, right? And so if we are now only looking 20 degrees, then the TH and the RH, in order to make sure that they are looking at each other, I need to have mechanical alignment. And also, once I do the mechanical alignment, if I want the TH to talk to some other RH or the RH to talk to some other TH, I have to mechanically steer the antenna, right? These are all viable things. So we are presenting them as challenges, but people do them, right? If you look at any mobile SATCOM link right now, the antenna is a high gain antenna that is mounted on a motor, right? And the motor tracks the satellite. And that way you're able to keep aligned with the satellite and be able to establish a SATCOM link. So people use these kinds of mechanically steered antennas all the time, right? But from a consumer application, that's heavy, expensive, and if we could avoid it, it would be great, right? So what that brings us to is the concept of doing this electronically. So we want to be able to electronically steer the beam from one direction to the other.